Hello, my name's Thanom and I'm from UNSW. Today I'm working through some of the Math 101 calculus questions from the section on numerical integration. In question 5, we're given a table of results from a chemical experiment. The results are the rate of formation of the chemical after 1 minute, 2 minutes, 3 minutes, all the way up to 8 minutes. So the rate, let's say that's something like grams per minute. It's the amount of chemical per minute, say, just because the time is given in minutes here. So after 1 minute, it was forming at 4 grams per minute. After 2 minutes, it was forming at 7 grams per minute, etc., all the way up to 8 minutes, it was forming at 24 grams per minute. So I've drawn that here. Now we want to estimate the amount of chemical formed from 0 to 8 seconds. They haven't actually told us what's happening at 0. We might just have to assume that it's forming at 0 grams per minute at the beginning of the experiment there. Now I've graphed that over here. What we need to realise is that it's the area under this graph that's actually going to give us the total amount of the chemical that's formed after 8 minutes. We can see just units-wise, that makes sense. If I multiply grams per minute by minutes, I will get the units of grams, so it makes sense that it would be an amount there. But you can also see its area. If we just took one value, let's say it was forming at 24 grams per minute for the whole 8 minutes, well, that would just be a straight line across here, 24 grams per minute for 8 minutes. Well, we would multiply those two values. Multiplying 8 by 24 does indeed give you the area there, and it does indeed give you the total amount of chemical that would have been formed. So what we're really after is the area under the function. We don't really know what the function is doing. Between these minute values, it could have been doing kind of something crazy. We don't really know, right? But we're just approximating the area under the graph, and we're going to do that using Simpsons Rule, and the area under the graph there is going to give us the amount of chemical formed. Okay, so if we want to use Simpsons Rule, we need some subintervals here. Presumably we want to use all the subintervals all the information that we've been given. So we'll divide it into subintervals that have a width of 1. So if it has a width of 1, then that's what I'll write h equals 1. So the width of each of these subintervals is going to be 1 there. Now what Simpsons Rule does, Simpsons Rule just uses 2 panels at a time, 2 subintervals at a time. So for this first subinterval here, what we're doing is we're approximating the area under our graph with the area under the parabola that would go through those 3 points. So Simpsons Rule will find the area under the parabola through those 3 points and use that as an approximation to that area under the graph. Okay, so we'll have to use Simpsons Rule a couple of times. We'll have to use it for this pair here. Then there's another parabola through those 3 points. So we'll use it for this panel here. There's another parabola through those 3 points. And there's another parabola through those 3 points there. So we'll have to apply Simpsons Rule 4 times if we want to use all the information that we were given in the question. I'm going to label these function values. I might label them y0, y1, y2, y3, y4, y5, 6, 7 and 8. So they're the function values at each of the points that we have. So Simpsons Rule, actually let's just write down the amount of chemical B formed, that is the area under the graph that we just drew, and according to Simpsons Rule, that's approximately h on 3. So this first pair of subintervals here, it's h on 3 outside of y0 plus 4y1 plus y2. That's this first pair of intervals here. The second pair of subintervals will be finding h on 3 outside of y2 plus 4y3 plus a y4. So h on 3 outside of y2 plus 4y3 plus y4. For the next pair, we have h on 3 outside of y4 plus 4y5 plus y6. And then for the last pair of subintervals, we have h on 3 outside of y6 plus 4y7 plus y8 there. So we're doing it for 4 separate pairs of subintervals. Now you can simplify this expression. If we take h on 3 outside the front, then we have y0 plus 4y1. y2 plus y2 will have 2 y2s, 4 y3s, 2 y4s here, 4 y5s, 2 y6s, 4 y7s, and a y8. So you can simplify it there if you wish. Let's substitute in our values. So h is the width of our strip, which is 1. And our y values are given according to this table. Remember, the first y value we're assuming is 0 here. So we have 0 plus 4 lots of 4 plus 2 lots of the next y value plus 4 lots of the next y value, 2 lots of the next y value, 4 lots of the next y value, 2 17s, 4 22s, and a single 24 for the last y value there. So the area under the graph is approximately this, and that's using parabolas in each of these sections of 2 subintervals to approximate the area. And that value is 97 and 1/3. And if we were in grams per minute there, then this would have been grams of chemical B. So we had a table of values showing the rate at which the chemical was forming, and if I graphed the rate versus time, it was the area under that function that was going to give me the total amount of the chemical that was formed, and I was estimating the area under the function using Simpsons Rule. So Simpsons Rule just for a pair of subintervals is given by this formula, h for the width, h on 3, outside of the first y value, 4 times the middle y value plus the last y value, but we applied it 4 times over to each of those pairs of subintervals. So applying it 4 times over, you can simplify it if you wish. After substituting in the function values, we get a total of 97 1/3. So that's the area under this graph, or the amount of the chemical formed in those 8 minutes.